This video presents a novel approach to haptic teleoperation of UAVs using control barrier functions. Teleoperated UAVs can enable humans to inspect dangerous areas from a safe distance. However, when flying a UAV, a human will have reduced situational awareness of the remote environment, making it difficult to fly in cluttered environments. Haptic feedback in teleoperation has proven to help reduce collisions and improve operator situational awareness. However, previous methods can increase workload and sacrifice task efficiency. Although haptic feedback is applied to the system, the rate of the collisions still remains relatively high. Therefore, we designed a novel CBF haptic feedback to help the operator fly the UAV safely and efficiently. In this method, control barrier functions are used to find the safe control input that is as close as possible to the human's desired control inputs, while also meeting specified safety constraints. Haptic feedback is generated to guide the human towards the safe control input. This video shows how the CBF haptic feedback helps the human operator safely fly a UAV in a virtual environment. In order to evaluate the method, we designed a user study with 12 subjects. Each participant was asked to navigate a UAV to inspect 5 targets in a simulated environment. In this study, we compared our method with no haptic feedback and the parametric risk of fails method. We record the number of successful trials which ended when the UAV reached the final target, and the number of failed trials which ended when the UAV crashed into the wall and lost flight. The CBF method reduced the number of failures when compared to the other two methods. Among the successful trials, the distance traveled by the UAV when under the PRF condition was longer than the distance traveled under the other two conditions. Also, the CBF method has shorter trial time when compared to the PRF method. To evaluate workload and perceived task performance, participants are also required to measure their experience using the NASA Task Load Index. The results show that condition CBF has lower mental demand and effort compared to no haptic feedback. In addition, condition CBF has lower physical demand, temporal demand, and effort when compared with condition PRF. In this research, a novel CBF approach to generate haptic feedback for human operators teleoperating UAVs is presented. The results of the user study shows that generating haptic feedback using CBFs is a promising approach that can improve a human operator's ability to safely fly a UAV without sacrificing task efficiency.